This is Rico Sostoki. My Grantham ID is G001410058. Completing my project Capstone. I did my project Capstone on a heart simulator splitter. Basic concept is to have the patient simulator which simulates a human heart rhythm, and it outputs that to one of our transmitters, and that transmitter will broadcast that information or data back to our receiver and then be displayed here on the screen as a patient. The concept is we want to use one splitter to feed multiple transmitters. That way we don't have to have a simulator for each transmitter. So here are the transmitters, and you can see that they have 5 leads. You can test the human heart rate with 3 leads, 5 leads, 12 leads. Typically in our applications we test it with 3 or 5 leads. So here's our patient simulator splitter. We've combined all those wires and into this box, and we also were able to simulate all 8 transmitters off of the one simulator. So it was pretty cool, the overall project. We also have some other things that we test because we want to be able to test and see if, like, a patient's lead gets disconnected. We want to know that it's not a failure, but rather it's some sort of lead problem. So the black and brown leads are called MCL leads, and then the white and red leads are called lead 2. Those are medical terms. At any rate, so if we disconnect the black lead, we should see an MCL fault pop up, which we do. So that works as expected. We also should be able to, if we disconnect the white lead, the lead 2, and you'll notice our signal just totally evaporates or goes kind of nutty, but we also have a lead fault 2 now. And once we correct these, we'll see a normal heart rhythm come back, and the leads are good. There's no errors. We could do the same for the brown. We notice the MCL fault, and then we disconnect the red lead and lead fault 2. So this was not originally in the scope of the project. This was added as we began our design because it just speeds up our testing process. Now, in addition to the fact that we're testing all of our transmitters at 80 beats a minute, we can also test every single one of them for that lead fault detection, which we're required to do. So that's the result of our project. All right, I'm going to go ahead and open up the simulator splitter so you can see the inside. This was the design. And the scope, the original scope by my shareholder was just to develop the simulator splitter. Like I said, I added the extra stuff in there. All right. So you can see, because we're working with such low levels, this, wow, is very sensitive. Low voltage levels, it's very sensitive to interference. But you can see inside here, so basic concept is we brought the simulator in, and then we have to wire it to our switches, and then from our switches out to the leads. So that was the basic concept with that. We had several different versions of this. This is the final product. So throughout the course of this, there were some improvements in design that I was able to implement. So here was my proof of concept, which was my first go-round. So basically I took, the only thing the supplier had was the 3 lead, so that's what I did my proof of concept with, was a 3 lead. Obviously we've got all 5 leads on the finished version, but you can see that I wasn't able to get too terribly far with it. He only had 3 of the connectors, and so but it did prove that the design would work, which was all we were really going after. So first things first, we have our patient simulator. The amplitude, which is pretty typical, is 1 millivolt. The heart rate that we're going to be using is 80 beats per minute, which is just a standard heart rate. And the ST would be if there was some sort of problem. We're not going to introduce any problem. We're just going to say this is a normal sinus rhythm at 1 millivolt at 80 beats per minute. So once we pump that out to our transmitters, we should see 80 beats a minute, and you'll see that they kind of flicker between 79 and 80, but it's plus or minus 1, which is really, really accurate. So that's nice. So we're pumping the signal out of our simulator into our splitter box and then out to 8 transmitters. So you can see here we have 8 transmitters. They're all transmitting on different frequencies. These frequencies were picked just on randomness. The frequencies used are in the 608 to 614 range. That's the range of medical devices. So we're in that range. We've set all these to various frequencies. I believe we used 608.10 through 609.20 was the range that we actually used. And so we send all those out back onto this screen, and we have 8 results. So if I were to remove power from one of these transmitters, we would notice that we have sig loss. So it's basically saying we've lost transmission. So we're able to verify that individual channels are done. Now I'm going to put the cap back on and we'll see the signal come back. Great. So we're able to verify all of our channels, and that in fact we are getting the proper outputs, and that the MCL and leads are going to function as we expect. Cabling is a specialized connector that hook up to patient electrodes. They also have those, you can see that they're color coded, and they have that special clip connector. The other end of the connector is a 2-lead which plugs into the transmitter. So one of these leads is actually relaying the signal information, and the other lead is an antenna, is used as an antenna. So the shielding for this cable, if you look in here, so when we first start, you can see that the cable has the metal insulation there. That's what we use for the antenna. It does have the center conductor wrapped in that plastic protective sheathing. That's what actually carries the signal. So during the process, what we're going to do is we're going to trim away the antenna portion, which we're not concerned with, and we're going to focus in on the signal portion. And this is a cable that's already been pre-done. We've cut it back. We've ensured that no antenna portion is up anywhere near the signal, because that will cause noise or interference. That's what happened in the first part of our project. This shielding was not trimmed back like it is here, and we had some signal problems. So this step's super important. So this is our connector. You can see here we ended up going with these Phoenix connectors. I liked them from the very beginning. It's a very compact design. It's got that specialized tip and indention, and then it's got the pin out in the middle. Now this is a 6-conductor cable. We chose 6 feet for our length, but it's a 6-conductor cable, and thankfully for us, most of the colors line up with what we're trying to accomplish. So you can see here we have brown, white, black, gray, pink, and blue. So we ended up using red as pink and gray as green, and we cut blue away, and it's not used at all. So I did develop a pinout sheet, which is shown there, so that we would know which pin is where. You can see channel 1, the frequency here is 608.10 megahertz. Channel 2 is at 608.20 megahertz. Channel 3 is 608.30. Channel 4 is 608.40. Channel 5 is 608.50. Channel 6 is 608.60. channel 7 is 608.70, and channel 8 is 608.80. So those are our frequencies. This is channel 8. As we can see here, we can see that channel 8 is in fact broadcasting a signal. And according to this, it should be at 608.80. So we'll check it on a spectrum analyzer, looking at the frequency of 608.80. And let's clean that up a little bit. So we can see our signal here. It's transmitting at 608.7998. That's the accuracy of our transmission. You can see a nice carrier with the sideband. So that's the data that we're actually sending to our receiver, and everything looks good. Signal strength is -56 dBm, which is fine considering we've cut all the antennas off. Cool. Just a recap of the overall project. The original project, the problem was we were having to use one simulator and test one transmitter at the same time. So the goal was to be able to use one simulator and test multiple transmitters. That was the goal, the original scope of the project. In doing our design, we have a transmitter that transmits information. And typically this would be hooked up directly to the simulator. During the course of our testing that we have to do, we also have to remove these leads to make sure that the software will detect those lead faults. So we'd have to physically go in here one by one and pull the lead and make sure that the MCL pops up, and then pull the lead and make sure that lead fault 2 pops up, which it does, but we have to do that on every single transmitter. So while we were designing, we decided we would add these switches to make that happen a lot faster. And so we, in addition to the fact that we've split the project, that we accomplished the project, we also sped up our testing. So it was a win-win all the way around. You can see here I'm testing on channel 5. But basic concept, we have our transmitter that transmits human heart rhythm, detects it, transmits it out to our central station. Our central station relays that information back in and gives us a nice pretty signal. So thanks so much, and enjoyed this Capstone project.